In this video, we are going to begin to explore the reactions of amines as bases with acids in order to yield amine salts or ammonium salts, which we learned to name in the previous video. These reactions are important, particularly in drug development, because the water solubility of amines increases dramatically when we react it with an acid to form the salt, because salts are generally more water soluble than molecules that have no formal charges. In other words, as we go from what I'll plug in here as just R3N, where R is a hydrogen or a carbon of an alkyl group, and we're comparing the solubility of that to, we'll say, R3NH plus, where now we have a positive formal charge. This has much better water solubility. And when developing drugs, one key consideration is that it's generally desirable for the molecule to be water soluble because it's going to facilitate the administration of that drug orally. And lots of drug molecules have amine groups. So as a result, it's a very common thing for the drug to be supplied rather than as just the drug itself, instead as its salt form. And you will commonly see that on the packaging of drug molecules by seeing the drug name listed, whatever that drug is, times HCl, which indicates that the drug, often with an amine functional group present in it, has been reacted with HCl to convert the drug, the amine, into the salt form to make the drug more orally bioavailable. For example, if we look at the bottle of Zoloft, a commonly prescribed anti-anxiety, antidepressant drug, we see that the chemical present in Zoloft is this, sertraline HCl, indicating that the sertraline molecule, or the Zoloft molecule, shown here, has been reacted with HCl to give the amine salt, or the ammonium salt form. Likewise, with Benadryl, we see the packaging says that it is diphenylhydramine HCl, indicating again to us that the drug diphenylhydramine, which is shown here, has been reacted with HCl. So in the reaction with HCl, if we have an amine group, since amines are basic, what will happen is that the amine will use its lone pair of electrons to come over and attack the proton from the acid HCl. And so we can show that happening here for sertraline by taking the lone pair of electrons from the nitrogen, bring those over to grab that proton from the acid, forcing the hydrogen-chlorine bond to break. And as a result of that, we end up with a product that now has that extra proton on the nitrogen. So now the nitrogen no longer is NH2, but now it's NH3. And further, if we calculate the formal charge, it's going to be +1. I'm not going to fill in the rest of the structure here just in the interest of not having to draw a whole bunch of other stuff out, but be aware those squiggly lines I've put are the bonds to other groups here that are bonded here. And so the outcome of this is that as a result of that protonation, the water solubility of the molecule will increase. And so by increasing the water solubility, we make the compound more orally bioavailable. Similarly, we can look at our structure of diphenhydramine over on the right, our Benadryl, in other words, and we can show how that will react with HCl analogously. In our diphenhydramine, we see our nitrogen atom. We bring that lone pair of electrons over to grab a proton from the acid, and that's going to create our salt product, where our nitrogen no longer has those 3 alkyl groups bonded to it as the only things bonded to it. Instead, now it also has the additional hydrogen, conferring a positive formal charge. That will also increase the water solubility of the molecule. We also need to keep in mind here that there is a counter ion in each of these cases, and that is the chloride anion. So to be complete about showing the product, in both of these cases, we need to include that Cl- as well. Now, do keep in mind that since amines are relatively weak bases, it's necessary that we react them with a relatively strong acid such as HCl in order for the equilibrium of this reaction to favor the formation of the HCl salt rather than the equilibrium favoring maintenance of the amine group. And so that's why generally in these reactions we use a relatively strong acid such as HCl to ensure that we get full protonation to create the salt products of these. Now, there are specific structural features of amine groups that can make them more strongly basic or more weakly basic. And that's what we're going to look at in the next videos. We are going to look at amine groups in various different contexts, meaning primary versus secondary versus tertiary, or associated with aromatic molecules or not associated with aromatic molecules, to determine what impact the position of the amine group or the structure of the molecule that has the amine group will play in determining how strong or weak of a base that particular amine group is. In other words, how readily will that amine group react to give an equilibrium that favors the product side in the formation of a salt molecule.